So, welcome to lecture 9. In the last class, we have learned how to carry out the product of symmetry operations or combination of symmetry operations, and we have also seen how to actually find out the complete set of symmetry operations a molecule may have, right? So, we have already seen that how to identify or how to find out a complete set. What do you mean by complete set of symmetry operations? So, now let's see what is a point group or symmetry point group, because our goal is to find out what is a symmetry point group, right? Symmetry point group. So a group of elements, so each member of the group is called as element. A group of elements or collection of elements, in this particular case each element is nothing but symmetry operation. Symmetry operations. So elements are not to be confused with, so I will write it as not to be confused with symmetry elements. Okay, so these are group elements which are nothing but symmetry operations. Okay, so a group of elements, in this case symmetry operations, and not to be confused with symmetry elements, that are interrelated according to certain rules. So what are these rules? We will see that. So the first rule is called as, there are four rules which define, which relate the elements and that defines a symmetry point group. The first property is, or first rule is called as closure, and it states the product, or in some books it is also written as combination of any two elements, and I will again write down that these elements are symmetry operations. So the product of any two elements in the group and the square of each element must be an element in the group. So this we have already seen using an example of BF3, that if we take list down all the symmetry operations and we take different combinations or square of any element, it must form an element in the group. It cannot go out of that group. So this is called as closure property, that it's a closed group. It is not infinite. I mean, there can be infinite symmetry operations, but again, those symmetry operations within that set must be closed, must follow the closure property, right? Also, it is not necessary that AB is equal to C and is equal to BA. That may or may not exist. So this may be the case that it is actually not equal and BA is equal to D. In this case, the group should have A, B, C, D in that set. Okay, so the elements C and D must be present if the commutation is not holding. So basically any order of combination must result into an element which forms the part of the group. Okay, there is one particular group called as abelian group. Group has all members or all elements follow commutation law, commutative property, we can say. So in that case, AB is equal to C, and that is equal to BA for uh, all the elements of the group. So that group is called as abelian group, that we will see later. So now we can use any particular molecule, take any molecule, list down all the symmetry operations, test for closure property. You should be able to do that now, right? Okay. Second definition is, let me go to second page. One element in the group, one element in the group must commute with all others and leave the element unchanged. We will see what it means mathematically. The element is designated as identity element. So we know that each molecule has the identity element in it, right? Defined as E. So we can say that if we take combination of Ex, X is another element, or Xe, it should give you X back. So one element in the group must commute with all other elements. That means E is commuting with X in this case, and leave the element unchanged. So it will result into X. So this is easy to show. You can take any molecule, do a symmetry operations, perform identity operation, and then do it in reverse order and see if it is equal to just the operation. So I will just take one example over here, which is, I know it is very easy to follow, but just in case. So let's say if I do C3 operation, what I will get is, I will not go into details, but what I will do is 3, 1, 2, and now if I do E operation, I will get same thing back. So F2, F3, F1, right? So this is the case of C3E. Now it is easier to see that this is equal to C3E and it's equal to C3, right? So an element must commute with all other elements and leave the element unchanged. Okay. So again, by element, when I'm saying element, I mean symmetry operation, not the symmetry element. This is the group element we are talking about. Okay, so third property is, so first property was closure, another is the presence of identity, which is always there. So symmetry operations do follow the two properties. Now let's say the third property. So third is the associative law of multiplication, which in this case is called as combination, because you cannot really multiply the symmetry operations, you can combine them, must hold, right? So this we have already seen that the symmetry operations do follow the associative law of combination, right? In the last class we have seen that. So this must hold, and that holds for symmetry operations. So again, this can be tested out easily. And the fourth is, every element must have an inverse, and the inverse should also be, which is also an element of the group. So every element should have an inverse, and that inverse should always be present in the group. So for example, again going back to BF3 example, we saw that C3 is equal to C3 square inverse. So C3 has an inverse which is C3 square, and C3 square is actually present as an independent operation in the group, right? So this property should hold for all the elements. So sigma V1, C2, any operation which is there, it should have an inverse, and the inverse should also be an element of the group. Okay, so you can take it as a home assignment. Using H2O, show all the symmetry operations in H2O follow the above 4 rules. Okay, so one by one you can actually do that and see for yourself whether it is true or not. Okay, so that once the symmetry operations, you have shown that they follow the above rules, these are called as point groups. That particular set of elements is called as symmetry point groups. Why it is called as point group actually? So why point group? It is because in all these symmetry operations, at least one point in the molecule in space is unchanged. So the location of that particular point remains unchanged. So that's why it is called as point group. At least one point in the molecule in space is unchanged uh, after performing all the symmetry operations. So you can pick up any symmetry operations of the group, and by performing any symmetry operations, at least one common point should be there which should not change in the molecule, and that's why this particular group is called as point group. So this is in relation to space groups, where the, like, when we study, or if you have actually gone through a course of crystallography where the translational operations are also there. So here we have seen that it's only rotation and reflection operations. So in crystallographic point groups, which are called as space groups, we also have something called as translational operations, so which is out of the purview of this course, but those are called as space groups, and these are called as point groups. So we'll not be discussing space groups in this course. We'll be only restricting ourselves to point groups, but there is more to symmetry basically, that's which goes to explain the crystallographic space groups. Okay, so now let's look at next is so now that we have learned what is a point group and how a point group is formed, let's see what are different types of point groups. So the next topic is Schoenflies notations of point group. Okay, the name of the how do you actually give names to different point groups. So let's see what are different point groups. Let us categorize them first, and then we will see what are their names and what are the elements required to define one particular point group. So the first in this category is called as non-rotational point group or point groups. These are generally low symmetry groups. So number of symmetry elements or symmetry operations are relatively lower. So let me point group list down and then the elements of the group, and I will also give you a little description. And let's see example. The first in this case is C1. C1 is when you have nothing but just the identity present. Okay, there is no other operation, no principal axis, no sigma, no I, no improper axis. So molecule having no symmetry basically. Molecule having no symmetry is called as C1 point group. Example can be when you have let's say if you have all four atoms of a tetrahedral are different. So you can say A, B, C, D, right? So in this case, the only the complete group is just E, and we can say that the order of the group is the number of symmetry operations present in the group. Okay, order of the group in this case is 1. Okay, so order is equal to number of symmetry operations, non-redundant symmetry operations is equal to order, which is in this case is 1. Okay, so next example, so non-rotational of course, because there is no rotation involved in any of this. Next is CS. So in this case you have E and sigma. Now sigma can be, mostly it is like a molecular plane. Molecule possesses only plane of symmetry as an element. So an example you can take is, for example, here we have Br, F, Cl, and this will be E and sigma H, right? And the order will be 2. So this is CS point group. Let's go to the next non-rotational point group, which is called as Ci. So as it is clear from the name, it should have E and I. So only inversion center. So only inversion center is present. Example is let's see if I can draw it correctly. So it's a staggered fluoro-chloro Cl, F goes into opposite H. So if you see, I lies in the middle of CC bond, and that's the only symmetry element present. There is no other plane, nothing is present, right? No rotation axis. Order again is 2 in this case because the two elements of the group are E and I. So this is all for non-rotational point group. So now let's look at second category, which is single axis rotational groups. So n of course cannot be 1 because we have seen that if it is 1 it will be C1, C1 point group. So n can be 2, 3 up to infinity. Okay, so we can say the point group is Cn point group. The elements are Cn and E, whereas the operations will be, so Cn will give rise to n operations. So Cn1, Cn2, and then up to Cn n minus 1, because Cnn will be again E. So these are the set of operations. So an example is open book structure of H2O2. So the structure looks like this. So let's say So here my C2 axis is actually perpendicular to the plane of the board, and the rotation is right. So O will replace with O, H will be replaced with H, right? So this particular group is called as C2 point group. So Cn basically, so the elements group elements will be E and C2, nothing else, because C2 square will be again E, right? Okay. So that is single axis rotational point group Cn. Uh, Another example for Cn can include hydrazine. Hydrazine is N2H4, and the structure you can draw in Newman projection. Let me draw as so if I draw it, let me see if I correctly draw it. H, H, and this is N, and the back N atom is also drawn like this, and then you have HH. Okay, so here the C2 will be passing through NN bond, right? So if you do this, so I would advise you to actually go to chemtube3d.com and look at this molecule in 3D, so that you can actually see where the symmetry operation lies, or where the position of C2 axis is. Okay, so that way it will be easier to see. But if you do this, so there'll be basically C2 which is passing through NN bond, and the operation will be like this. So this will be your C2 axis. So this H goes at the back, this H, this will be the kind of rotation we're talking about. Okay, let's take one more example for this, which is triphenyl phosphine. So in this case it is phosphorus atom, and then you have three phenyl rings which are oriented like a propeller. So none of these phenyl ring is actually in the plane of the molecule. So if I draw it more precisely, it's like something like this, where this bond is actually coming out of the plane of the board, and this bond is going below. Okay, so it's like something like a propeller blade, uh, fan like of thing, which is twisted phenyl ring. So there is no sigma H in this case. Okay, so here the symmetry axis is like this C3. Okay, so all of these form CN point groups. So next is CNV point group. So here molecule possesses a CN axis and N vertical planes that are collinear with CN axis. So the operations will be E, Cn, Cn2 up to Cn n minus 1, and we should have n sigma v's. Okay, it can be sigma v1, sigma v2, and so on. Okay, so example, we have already discussed these kind of examples. So one is water. So water has C2 axis and two sigma v's, which are collinear with Cn axis. Then similarly NH3, has a C3 axis and 3 sigma V's collinear with the C3 axis, and so on. So these are C and V point groups, right? So we can also see what is the order of this particular group. So order here is 4, for example, and we can work out the order for NH3. Okay. Then next single axis rotational point group is CNH. So here the group elements are or the symmetry elements are E, Cn, sigma H. This is the least which is required. So molecule should possess at least a Cn axis, and of course it will generate n operations, and a horizontal plane perpendicular to Cn axis. Okay, so for example, let's look at B OH OH. Everything is in plane. There is a C3 axis which is perpendicular to the plane of the board, so C3, and there is a molecular plane which is sigma H, right? So because C3 and sigma H are present, so there would also be a S3 axis, and of course E would be present. So these are the set of symmetry elements, and the corresponding symmetry operations will give rise to 2 and 2 here, right? So 2C3 E, 2C3 sigma H, and 2S3, and so on. Okay. Another example you can look in this category is CCH Cl H Cl. So here the elements are E, C2, sigma H, and because C2 and sigma H are present, so there would be S2, which is nothing but I, and the operations would include E, C2, sigma H, I. Yeah, because C2 square will be equal to E only. So these are the set of operations. So you can say E, C2, sigma H, and I will be present. And then let's also discuss one special group under single axis, which is called as C infinity V. So these are basically non-centrosymmetric. It is easier to remember like this: non-centrosymmetric linear molecules. So example is HCl, anything linear without having any center of symmetry. Or let's say we have COS or CSO. Okay, so the elements will be E, C infinity. We can see that there is a C infinity axis passing through the linear axis of the molecule, and infinity sigma V's. So infinity sigma V's are all sigma V's which are containing that particular C infinity axis, right? And we can find out the corresponding operations. There will be infinity operations arising because of C infinity. Okay, so that's it for today. We will next discuss dihedral and cubic point groups, and then we will also see a flow chart how to discuss how to actually identify which molecule belongs to which particular point group. Okay, so that's it for today. So do practice, look at different molecules, list down symmetry elements, and then try to work out if the operations present in that molecule are actually following all 4 properties of the group or not. Okay, thank you.